Welcome to The Explainer. Today, we're going to talk about something pretty amazing, photochemistry. It's all about how light isn't just, well, for seeing stuff. It's actually a super powerful tool that can make chemical reactions happen. So let's kick things off with a question for you. Think about this for a second. What could photosynthesis, the way your eyes work, and your body making vitamin D possibly have in common? I mean, they seem totally different, right?
Well, the answer is pretty incredible. They're all powered by the chemistry of light. Yep, every single one of those processes is driven by photochemistry. These are reactions that don't get started by heat like most reactions you might think of, but by the energy packed inside light itself.
And that's really what photochemistry is all about, right? It's the branch of chemistry that looks at the chemical effects of light. Basically, what happens when light hits stuff. See, when a molecule absorbs a photon, that's a tiny little packet of light energy, it can kickstart a whole chemical reaction. It can change that molecule in ways that, honestly, you just couldn't do any other way.
Okay, so how does this actually work? It might sound complicated, but the entire field is really built on just two main rules. Two golden rules, you could say. And if you get these, you've pretty much got the key to understanding all of photochemistry.
All right, rule number one. It's called the Grothus-Draper law, and it's actually super simple and makes perfect sense. It says that only the light that gets absorbed by a molecule can actually do anything. You could shine the most powerful laser in the world at something, but if the molecules don't soak up that light, nothing, nada. The light has to be captured to kick off a reaction.
And this is exactly how scientists figure that out in a lab. They use a machine called a spectrophotometer. It shines a beam of light through a sample, and then a little detector on the other side measures how much of that light made it out. So you just subtract the light that came out from the light that went in, and bam, you know exactly how much was absorbed. And remember, that's the light that's doing all the heavy lifting.
Now for the second rule, this Stark-Einstein law. This one's all about numbers, and it's really clear. One photon of light energizes one molecule. That's it. It's a perfect one-for-one deal. Every time a molecule absorbs a single photon, that one molecule gets excited and ready to react. It's a super important fundamental step.
So, okay, this leads to the obvious next question, right? A molecule absorbs a photon, it gets all this extra energy, then what? What does it actually do in that split second after it gets zapped with light?
And this is where it gets really, really cool. What you're looking at here is a Jablonski diagram. It's basically a roadmap of all the different things that can happen to that energized molecule. See, when it absorbs that photon, one of its electrons literally jumps up to a higher energy level. We call that an excited state. You can kind of think of it like tossing a ball way up in the air. But you know, what goes up has to come down. And how it comes down is what makes all the difference.
So one option is for the molecule to just release that energy back out as light. If the electron takes a quick direct path back down, it gives off a little flash almost instantly. That's fluorescence. But sometimes it takes a weirder, more complicated path back down, a forbidden one, as chemists say. The electron kind of gets trapped for a little while, and the energy just slowly leaks out over time. That slow, delayed glow, that's phosphorescence. Yeah, just like your old glow-in-the-dark stars on your ceiling.
Okay, so let's recap. We've got our rules. One photon gets absorbed, one molecule gets excited. But here's the thing. Just because a molecule gets excited doesn't guarantee it'll go on to form the final product we want. Some of them might just release the energy as light, right? So, how do we measure how efficient the whole reaction is? How much bang are we getting for our buck?
Well, to figure that out, scientists use something called quantum yield. Don't let the name scare you. It's actually a really simple idea. It's just a ratio. You're asking, for every single photon that got absorbed, how many molecules of my product did I actually make? It's the perfect way to measure how efficient the whole process is.
And check this out. This is where it gets wild. The quantum yield can be completely different from one reaction to another. Look at hydrogen and bromine. The yield is tiny, just 0.01. But then you look at hydrogen and chlorine, and whoa, the quantum yield is over 100,000. So what's going on? Well, in that case, one single photon kicks off a massive chain reaction. It's like a domino effect, where that one excited molecule causes thousands and thousands of others to react. So that initial one-to-one rule can have dramatically different results down the line.
So, let's zoom out a bit. We've got the rules, we've got the mechanics. Now let's talk about the impact. Where does all this show up in the real world, in nature, and in the tech we use every day? And why is it such a big deal to use light to start a reaction?
Okay, this is maybe the most important takeaway. Think about normal reactions, the ones driven by heat. They happen because molecules are just randomly bumping into each other. They're always going to take the easiest, laziest path. But photochemistry, it's a game changer.
You're not just heating everything up randomly. You're using light to inject a very specific amount of energy into a very specific molecule. This lets you access these really high-energy pathways and make things that are non-spontaneous, stuff that, nature just wouldn't make on its own if you just added heat.
And of course, nature is the absolute master of this. I mean, look at photosynthesis. It uses sunlight to force a reaction that would never happen on its own, turning CO2 and water into sugar, the fuel for life. And the way you see, that's a molecule in your eye, rhodopsin, changing its shape when light hits it. Even a firefly's glow, that's a chemical reaction releasing its extra energy as light. It's all photochemistry. And we humans have gotten pretty clever at using it too. We've harnessed this power for some unbelievable things. Take medicine. There's something called photodynamic therapy, where doctors use lasers to turn on a drug right inside a tumor to kill cancer cells. And you know that microchip in your phone? Every single one is made using photochemistry to carve out those tiny, tiny circuits. We're using it to make life-saving medicines and even the plastics all around us.
So this really leaves us with a huge, exciting question, doesn't it? As we get better and better at controlling the chemistry of light, what else could we do? We have this incredibly precise, powerful, and clean tool to make molecules do what we want. We can build things with almost surgical precision, things we once thought were totally impossible. So the real question isn't just about what we're doing now, it's about what impossible reactions we're going to unlock next.